Have you ever wondered why primes just keep showing up like weeds? Why they have a seemingly no pattern? Well, I'm about to show you how these mysterious numbers could very well be explained by the energy levels of atoms. The Riemann hypothesis and dynamical system. But before we start on this fascinating connection, it is necessary to make a few definitions. The Riemann hypothesis is a conjecture that the Riemann zeta function, the function you see at the top, has its zeros only at the negative even integers and complex numbers with a real part of 1/2. It was proposed by Bernard Riemann, after whom it is named. The Riemann hypothesis implies results about the distribution of prime numbers, which is why it's so important. Along with suitable generalizations, some mathematicians consider it the most important unresolved problem in pure mathematics. Now, the nucleus of a heavy element is a particular beast. The whole blob is teetering on the edge of instability. Now this nucleus, this wobbling blob, consists of a number of states, some having high energy, some having low energy. This type of problem exists in a larger class of problem called dynamical systems. Here's an example of a random Hermitian matrix. You can see that there are complex numbers and real numbers. Things we need to know about the random Hermitian matrix. One is that the green and purple numbers are complex conjugate of each other. Two, that all eigenvalues are real. And if you're wondering what an eigenvalue is, the eigenvalues are the zeros of the characteristic polynomial of the matrix. Numbers may seem random, but they are picked from a Gaussian normal distribution. The eigenvalues of random Hermitian matrices turn out to be a great fit for the energy levels of heavy nuclei when observed in experiments. Eigenvalues of random Hermitian matrices showed repulsion. Energy levels trying to get as far as possible from each other, like a long-standing line of antisocial people. The Hilbert-Boyle conjecture states that the non-trivial zeros of the Riemann zeta function correspond to the eigenvalues of some Hermitian operator. Montgomery-Odlyzko law says that the distribution of the spacings between the successive non-trivial zeros of the Riemann zeta function is statistically identical to the distribution of eigenvalue spacings in a GU operator. Already explained that the definition of repulsion is that energy levels trying to get as far as possible from each other, like a long-standing line of antisocial people. Well, this trait can be seen with the zeros of the zeta function and the eigenvalues of Gaussian random Hermitian matrices. We can already see that the energy levels of nuclei of heavy elements can be demonstrated by the eigenvalues of random Hermitian matrices, and that the eigenvalues of random Hermitian matrices show repulsions, as do the zeros of the zeta function. So we can say that they are quite similar. Non-trivial zeros of Riemann zeta function arise from inquiries into the distribution of prime numbers. The eigenvalues of random Hermitian matrices arise from inquiries into the behavior of subatomic particles under the laws of quantum mechanics. What on earth does the distribution of prime numbers have to do with the behavior of subatomic particles? Only time will tell.